Okay, so in this example, let's actually calculate some probabilities about when we might make mistakes and then actually see which of these probabilities we could attribute to which type of error. And so the situation I want to take a look at here is cholesterol level test. And so let's say for men that have a healthy cholesterol level, that we know that population cholesterol level has a mean of 180 and a standard deviation of 120, or excuse me, of 20. And on the other hand, if we take a look at men that are predisposed to have a heart disease, these men have a mean cholesterol level which is much higher, which is 300, and a standard deviation of 30. And what we know is that according to this test, if the cholesterol level is 225 or higher, then I'd say that you have heart disease. So this is the cutoff level clinically when a man is told that they have high cholesterol levels and that they might be predisposed to heart disease. Okay, so in part A, we want to calculate the probability they are diagnosed as predisposed given that the man is healthy. So what it means to be predisposed is we're going to calculate what is the probability X is going to denote the cholesterol level of a randomly selected person. So what's the probability that the cholesterol level of that randomly selected person is bigger than or equal to 225? And we have a given information here. So this is like a conditional probability given that we know X is normally distributed, given that we know this person is healthy. The mean of that group is 180 and the standard deviation is 20. So we want to calculate what's the probability that X is going to be bigger than or equal to 225, that a randomly selected healthy person is going to be told that they're predisposed to heart disease. So to calculate this, we could, for example, calculate the z-score of that value by taking the cutoff, 225, subtracting the mean, 180, and then standardizing this by dividing by 20. And that gives us a z-score under this assumed population, which is 2.25. And then we could calculate this probability, for example, by saying this is going to be 1 minus p norm, since we're going to the right, and our z-score is 2.25. And that comes out to be 0.0122. And what this probability represents is this is telling us really there's a 1.22% chance of telling a healthy person that they are not healthy. Okay, and moving on for part B, now we're asking what's the probability of making an error in the sense that we have a guy who actually is not healthy, so they're coming from the population that has a mean of 300. What is the odds that they actually have a cholesterol level which is less than or equal to 225, so they would be told that in fact they're healthy when they are not healthy. So here we're calculating what's the probability that X is less than or equal to 225, given that X, this person, is coming from a population which is normally distributed with a mean of 30 and a standard deviation, a mean of 300 and a standard deviation of 30. So here we again could calculate the z-score by taking this cutoff of 225, subtracting the mean from that population, which is 300, and then dividing by 30. So we're not working with sampling distributions here. We're picking a person at random from the population. So that's why we're just calculating the z-score using standard deviations and not worrying about standard errors. So this z-score winds up being minus 2.5. So we could calculate this by calculating the area to the left of minus 2.5 under the standard normal distribution. And this comes out to be 0.0062. So in other words, this is telling us that there's a 0.62% chance of falsely telling somebody they are healthy when they are not. So in other words, falsely telling a sick person they're healthy. Okay, so again, both of these errors are not good to make. We don't want to make errors in general, but this is all based on randomly selecting people, so sometimes we just get unlucky. So now we want to kind of think about each of these probabilities that we just calculated and which of these would represent a type 1 error, which of them might represent a type 2 error. So a type 1 error is getting a false positive. So type 1 error would be what's the probability of telling a healthy person that they're sick. So that was the first one that we calculated up here. And type 2 error is a false negative. So this would be what's the problem of telling somebody, telling them that you're fine and healthy when in fact that person is sick. So here is the type 2 error. And in this case, the type 2 error is about half as much as the type 1 error if we compare the 0.62% compared to the 1.22%. And so in this case, yeah, the type 2 error is probably worse to make in this scenario, so that's why they would want this error to be a little bit lower. But you can see how moving around the 225, changing what this level cutoff is to demarcate whether someone is healthy or predisposed to heart disease, is going to tell us what are the odds of making a type 1 error versus a type 2 error. So you can play around with that cholesterol level cutoff in order to somehow control for how likely is it to make a type 1 versus a type 2 error.